II back in your hands. The key is up on Moodle. Please go ahead and look at my answers and your answers and see if you try to understand where I took points off. You'll see, unlike many of the times I grade, I marked minus rather than, this was a subtractive grading rather than an additive grading, but it's the same thing. So if you disagree with where I took a point off, or more, let me know, and we can talk about it. But look at the answer key first. So the idea was that on Tuesday you were supposed to have watched the video from last year. Did that work? Were you able to understand the video? You know, the quality is not always perfect, but were you able to get information from the video? Okay, the PowerPoint's up there, the video is up there. We'll do some of it again, you know, in review today. And feel free to ask me questions. Patience. Joey? Thank you. Yeah. Okay. So we are making, well, you've already made the transition to talking about kidneys and the urinary system. This is my first opportunity to make that transition. Let's do some anatomy. Who wants the laser? Okay, so we're going to pass it around this way from Mackenzie. So pick something and give me a name. Then you can write it in on your sheet. That is the ureter. This would be the medulla, right? We might also call it the renal pyramid. Depending, and I don't remember what this particular is. So both of those would be correct for that label. Yes, sir? Okay, pass it along. No, let's see, I got this wrong. This is not the ureter.
It's right to the left.
Yeah. This is the ureter.
Yeah.
Did you point to this one? This?
No,
this?
The yellow tube.
The yellow tube. This is the ureter. This is not the ureter. It's got a different name. Okay? You can pick one.
That's the renal vein?
Exactly. That is the renal vein. Now, they color-coded blue. It's not actually blue, of course. And in figures that are grayscale, you couldn't tell the difference between the red and the blue on a grayscale. So I would accept either answer.
Oh, okay. That's what I'll do that.
So who's got it now? Claire? Tari? What's the name of this tube?
Oh, man. I was gonna, okay.
I'll pick something else. But that one's pretty easy.
I would have thought that was the renal vein. That too.
The red one?
Yeah. And I was gonna say that's the renal pelvis.
Okay, that is the renal pelvis.
But this is not the renal vein?
The red one?
Yeah.
Well, no, not really. If this is the renal vein, what is this?
Artery?
Yeah, the renal artery. But what I was saying is that in a grayscale, you can't tell them apart, and one is not always on top of the other. So I would accept either answer in either of these boxes in a grayscale.
Okay.
But if it's in color, yeah, then you would choose the red one to be the artery.
Okay.
Okay?
Right there is the cortex.
That is the cortex, or the renal cortex. I suppose we should write renal cortex because, of course, we have a cerebellar and a cerebral cortex, but that is the renal cortex. We also have a medulla oblongata, so we, in principle, should put in renal medulla. but I won't be a stickler about that. Alice? The last one?
Are those the calyces?
They are the calyces. So 1 calyx, 2 calyces. Okay? So there we are, some gross anatomy. We'll see that in lab today. Let's see if we got it right. Yes. Okay, so that's anatomy to learn for the next quiz, which is coming up today. The quiz will be available in the CSD desk today. It's due on Sunday. It will cover material that you learned this week, both from the video on Tuesday and from class today. So, the main point of the kidney is to make a filtrate from the blood. So it takes the blood and it creates a filtrate of it that has water and small molecules. What's going to happen then is the renal tubules, which we'll talk about anatomically in a moment, reabsorb the good stuff and leave the bad stuff to be excreted in urine. So it's a recycling system, or a reclamation system. Lots of things get filtered. The kidney takes back what you need and excretes the rest. So let's just talk, let me see what the next slide is. Yeah, we'll wait on that. So let's just talk about the volumes for a minute, because it's really amazing. So this is a beaker that has something like 5 liters. This volume represents your cardiac output per minute. Each minute, your heart pumps this volume of blood out the aorta and to the whole body. So each minute, this is the amount of blood going through the aorta and everywhere in the body. Cardiac output, 5 to 6 liters per minute. About 20% of that cardiac output of blood goes to the kidneys. So a large amount of blood goes to the kidneys. So 1/5, 20% of 5 liters is 1 liter. So this is the amount of blood that goes to the kidneys every minute. Blood is cells and plasma. You may have heard the expression hematocrit. Hematocrit is the percentage of your blood that is cells, mostly red blood cells. A typical hematocrit is about 55%. So about 45% of your blood is plasma. So this is the volume of plasma that is going to the kidneys every minute. Cells are not filtered, only small molecules. So that's why we're focusing on plasma, because the plasma is where the small molecules are. Glucose, sodium, bicarbonate, small but not large proteins in blood plasma. So 55% of 1 liter is 500 mils of plasma going to the kidneys every minute. The kidneys filter about 100 mils every minute. So 1/5 or so of the plasma that goes to the kidneys becomes filtrate, gets filtered out by the kidneys. 100 mils every minute. So in the 10 minutes that we have been sitting here, your kidneys have filtered a liter. So imagine how many times per minute you'd have to go, imagine how much you'd have to be going to the bathroom if we didn't do this reclamation thing. Every minute, your bladder would be filling up this much, so in about 3 to 5 minutes, you'd be running to the bathroom. The point is, the kidneys reclaim 99% of the water and the good stuff and you generate about 1 mil per minute of urine, plus or minus depending on the conditions. So 99% of the water and the stuff that's in the water that your kidneys filter, the 99% of the filtrate is reabsorbed, recovered by the kidney, and 1% is excreted. And that's why you can go for hours, not minutes, before you have to go urinate. Okay, so that's the sort of flow chart of what we're talking about. What we're going to talk about today is filtration. And next week we'll talk about reabsorption. Okay? So here is the microscopic anatomy of the kidney. It's called the nephron. The nephron is the functional unit of the kidney. It's sort of like, muscle and bone are the functional units of the muscular system. A neuron is a functional unit of the nervous system. The nephron is multicellular, more than one cell type. Many cells go into the nephron, and then millions, probably hundreds of thousands at least, of nephrons do the job of the kidney, the filtration job and the reabsorption job. So let's do this. Let's play this game. Who's got the laser? You already gave one, so pass it along. Pick a. Who's got it? Abby? Or are we just passing it around until some brave soul takes it?
I'll go. I have the laser.
Oh, okay. So pick a box and give me a name.
The glomerular.
Okay.
This thing.
So that is the glomerulus. Yes.
Oh, glomerulus.
So this structure here, this line here is the glomerulus. We get to say some good words in this section. Glomerulus. That is where filtration is going to happen. We're going to talk about glomerular filtration.
I have a question. Where do they make all these names from? Like, they just be coming up with the craziest names.
Yeah. Scientists, they knew Latin once upon a time. Many of these names come from Latin. Okay, let's do another one. Who wants to pick one?
This is the book of Henry.
Okay, good. So the book makes a big point about thick and thin elements of the loop of Henry, which I don't make a big deal about. We do have to think about the descending and ascending parts of the loop of Henry. So don't worry about thick and thin, but do worry about descending and ascending. So this one, it turns out, is the descending loop of Henry, descending limb of the loop of Henry. And this one is the ascending. And you'll see why loop of Henry. Oh, Henry is spelled H-E-N-L-E.
Oh.
Henry. Yes, okay. Who's next? Joey?
Right here, that's the vasa recta.
Good. That is the vasa recta. That is blood flow that parallels the loop of Henry. We'll talk about that next week.
Medulla.
Okay? This is the medulla.
Cortex.
Cortex. Cortex, okay? Sam, you want to pick one?
No.
They're going to get harder, so you can pass. Josh, you got the laser.
Medullary collecting duct?
Yes, the medullary collecting duct. Okay?
This is afferent and efferent arterioles.
Okay, right. So I can't reach. So let me get a laser. So this one. So here, this is a branch from the renal artery. So this is not. We'll take a point off if you call this the renal artery. That is not the renal artery. It is a microscopic branch from the renal artery. This, and here's an even smaller branch from the renal artery. So this is a branch from the renal artery, lots of things going off to other nephrons. Here's one, this one here, which is this box here, is the afferent. Arterial. Okay, the one going in to the glomerulus is the afferent arterial, and the one coming out of the glomerulus, this one here, well, whatever, this one here is the efferent arterial. Going in is afferent, going out is efferent. That's what brings the blood to the glomerulus for filtering. Okay, we're almost there. What goes in, what is this? So, who's got the laser? Yeah, do you want to choose one, or do you want me to pick one for you?
I can choose one.
Okay.
This is the Bowman capsule.
Okay, Bowman's capsule. Bowman's capsule is the outer thing that surrounds the glomerulus. Okay, who's next? Marina? We don't see the renal pelvis on this slide. Nope, the renal pelvis is down on the first floor.
Right there is the macula densa.
Okay, this junction right here, that junction between this yellow tube and the afferent and efferent arterial, can you see why I'm calling this one afferent? It's coming, here's the blood coming in, going through the glomerulus and coming out. So this is afferent, this is efferent. This thing, which we haven't named yet, well, we have named this the ascending limb of the loop of Henle. That junction is called the macula densa. We'll talk about the function of that junction next week. Okay? Anybody got a name? If this is the medullary collecting duct, what's this? We'll call it out. Cortical collecting duct. Cortical collecting duct. I think your book uses the word duct. I will sometimes use the word tubule. Interchangeable. What is, again, I can't reach it. What is this? The proximal tubule. Like thick and thin, I will not be getting into the weeds of convoluted versus straight. So this is the proximal tubule. Proximal because it is near the glomerulus. It is, right there is the beginning of the proximal tubule. So the proximal tubule comes out of the glomerulus. So if this is the proximal tubule, what is this? The distal tubule. Again, your book makes a point of distal convoluted versus distal straight. Proximal convoluted, don't worry about convolutions. I won't take your points off, but proximal and distal are an important distinction. So, this one was just thin, but remember we're not worrying about thin. So let's see if we got it right. Did I get everything? Oh, peritubular capillaries, right. So this is the vasa recta that surrounds the loop of Henle, and this network of capillaries that surrounds the glomerulus, the proximal tubule, and the distal tubule is the network of peritubular capillaries. Okay, rather than spend a lot of time erasing, I'm just going to put it on the screen. So the order of operation that we're going to be seeing for the next couple of weeks is blood flow, afferent arterial, glomerular filtration. Now we have to think about there's blood and there's filtrate. The blood is going to go into the efferent arterial and either go into the vasa recta or go into the peritubular capillaries, or both, depending on the branching. Okay? So the blood goes from the branch of the renal artery, afferent arterial, glomerulus, efferent arterial, and then vasa recta or peritubular capillaries, and then into the branch of the renal vein, where it will get circulated out of the kidney. That's the order of blood flow. The order of urine flow goes like this. In the glomerulus, the filtrate is formed in Bowman's space, the space between the glomerular capillaries and the Bowman's capsule. Filtrate, remember filtrate, 100 mils per minute, is formed in the millions of these glomeruli spaces. It gets processed through the proximal tubule, through the loop of Henle, descending and then ascending, the distal tubule, the cortical collecting tubule, and the medullary collecting tubule. And by the end of the medullary collecting tubule, we call it urine. Before that, it is not urine. You can call it tubular fluid, you can call it processed filtrate. I use the word tubular fluid most of the time. So we get 100 mils per minute of filtrate, and then we process it to get 1 mil per minute of urine, and in between, it's tubular fluid. Get to use the word tubular a lot, it's very fun. Questions about the anatomy and the processing that we're going to be talking about?
So from like this slide and from what you were saying in the first lecture that we had to watch, like is it true that the peritubular capillaries are only for cortical nephrons and then vasa recta are only for juxtamedullary nephrons, or?
I'm real careful about saying only. So, no, I mean, there would be a vasa recta here.
Okay.
On this short loop of Henle. And there's certainly peritubular capillaries around this set of tubules. So peritubular capillaries surround both types, both the cortical and the juxtamedullary nephrons. The only difference between those two types of nephrons is how deep the loop of Henle goes into the medulla. That's the only difference. They're functionally different. but let's not worry about that right now. So both types of nephrons have peritubular capillaries, and both types of nephrons have vasa recta. All right, let's do this one more time. Yes, I will. Okay. Some of these I can reach and some of these I can't. Who's got the laser? Pick a box. So what we're doing now is we're zooming in on the glomerulus, and there's anatomy there as well.
Is this whole thing a podocyte?
This pink thing with these fingers and this cell body is a podocyte. So this is where the podocyte goes. That's the cell body and the processes of when we see two podocytes. Okay? Some of these you know. You can figure these out. So here is blood coming in because here is blood coming out.
Yes.
So what is the name of this?
So it's an afferent.
That is the afferent arteriole. When I can't reach it, it's afferent. That's the afferent arteriole. Okay? So what's this one?
Oh, so the one
No,
coming out.
you can, somebody else can be on the spot. Andrew? You're getting away. What's this box here?
Efferent.
Efferent. Blood comes in the afferent, goes out the efferent. What do we call this junction between afferent, efferent, and the top of the ascending loop of Henle, which is really the beginning of the distal tubule? What do we call this thing? Macula densa. So I just gave you the name. This yellow thing is supposed to be the distal tubule. It's really the very beginning of the distal tubule, the end of the ascending limb of the loop of Henle. That's the distal tubule. This structure here is the macula densa. So this is the anatomical connection between the distal tubule and the afferent and the efferent arteriole. And these, does anyone know the names of the purple cells that form this connection between the afferent arteriole and the distal tubule? Juxta. Juxtaglomerular cells. So juxta means near. To juxtapose something is to put it on top of or near something. Juxta, near the glomerulus. Juxtaglomerular cells. Okay, so I can't reach some of these. What is this supposed to be pointing to? We've got the name down here. That's a podocyte, right? I mean, that's a podocyte. This is a podocyte. So this thing here so this box is actually pointing to two things. So the bottom part of this box is a podocyte. The top part of this box, this line here, is pointing to what? Bowman's capsule. The cells that make up Bowman's capsule. And your book makes a thing about the parietal layer and the visceral layer, and you know I make a deal about that when it comes to pleura, but I don't make a deal about that when it comes to glomeruli. So this is the Bowman's capsule. What is this space in between the glomerular capillaries and the Bowman's capsule? What's that space called? Bowman's space. Okay, so this space in here is where the filtrate first collects. So what's the name of this right here? That's the beginning of the proximal tubule. And what's the name of what goes in there? What is it, layer? It's a glomerular capillary. So this is a glomerular capillary. Now we have multiple types of capillaries. In your test, you labeled pulmonary capillaries that were surrounding an alveoli. Some of you just wrote capillary, and I didn't take points off for not saying pulmonary. But now I'm going to start taking points off. You know that there are systemic capillaries, pulmonary capillaries. Now we're talking about renal capillaries, in particular glomerular capillaries. I will want that name. So up here is the proximal tubule. Did I get them all? Oh, no, these things here. Okay, what do we call when these podocytes make this interdigitation with each other? So this is one podocyte, here's another podocyte. They make this structure that looks just like this. What do we call these spaces between these two podocytes? Filtration slits. And on the inside of the glomerular capillaries, so this is looking at from the outside. If we cut open the glomerular capillaries, we see these holes. They have a name, that isn't holes. What is the name of these structures? Fenestri. Which is Latin for window.
For the top, this one right here, is that supposed to be, what is that?
That's a glomerular capillary. It's labeling glomerular capillaries twice.
Okay.
Yeah. Okay? So are we good? So this is now the microscopic, right? If we go back, this is the macroscopic, the whole organ anatomy. This is the nephron microscopic anatomy. And this is the microscopic anatomy of the glomerulus. Any more questions? Okay, that review took a lot longer, but I want to make sure that we have the language of the anatomy going on here. Let's talk about filtration, because that's what we're doing today, glomerular filtration. Filtration is just pushing fluid through small holes, right? So we have these fenestri, and we have the filtration slits that are connected, that are on the outside, the inside, the outside of the glomerular capillaries, and we're going to collect this filtrate into this Bowman's space. The thing that makes fluid move is pressure. So the pressure in the glomerular capillaries favors filtration. We're just pressure, hydrostatic pressure. We have some hydrostatic pressure in Bowman's space, which opposes filtration. pressure in the capillaries favors filtration. Pressure in Bowman space opposes filtration. And we have this other thing called osmotic pressure. Osmosis. How many of you have done anything with osmosis in any class? Okay, so in which direction does fluid move by osmosis alone? Towards the higher concentration. Fluid moves from the dilute to the higher concentration. So as filtration happens, the amount of solute in the blood plasma increases. Why? It's because blood plasma has protein in it. You've heard of this protein, albumin. In cell-phys, you use bovine serum albumin. Remember in your Manduka project, that's cow blood protein. But you have human serum albumin in your serum, in your blood, and that's a solute. And it's at a high enough concentration that it pulls water in the direction opposite the pressure push. So pressure in the capillaries favors filtration. Pressure in Bowman's space opposes filtration. And solute in the blood opposes filtration. Those are the main forces that drive filtration. Now you could say, wait a second, what about solute in Bowman space? It's usually too small to make a big difference, but solute in Bowman space would favor filtration. Okay, let's do a clicker. This is an osmosis clicker. We're thinking about osmosis only, not hydrostatic pressure. Which way does water flow? Yes, so D is the obvious answer, and it turns out C is also correct. So when fluid is flowing from the solution that is dilute to the fluid that is concentrated, we say that the dilute fluid has the higher osmotic pressure because it forces water to flow into the concentrated. So it's counterintuitive. So if you think about concentration and then apply that to pressure, you'll be good. Osmosis pushes water from dilute to concentrated. Because water is flowing from dilute to concentrated, we say that the dilute solution has the higher osmotic pressure. That's just part of the language. I wish it were, it's not completely intuitive. Glomerular filtration is controlled. Let's talk about the control of glomerular filtration. So here's a cartoon of an afferent arteriole and efferent arteriole. I know that this is afferent because it says AA, so this is the afferent arteriole. Blood is flowing in this direction, there's the blood flow. This little V is supposed to indicate all those glomerular capillaries. So afferent arteriole, glomerular capillaries, efferent arteriole. Here is the cartoon of Bowman's space. What is this the cartoon of? This is Bowman's space. What is this supposed to be? It's proximal tubule, from which we will then process the tubular fluid. If we constrict the afferent arteriole, what cell type would constrict the afferent arteriole? Vascular smooth muscle. I could ask you to tell me the mechanism by which vascular smooth muscle constricts the afferent arteriole. I did that once. I'm not above doing it again. If you constrict the afferent arteriole, that reduces the pressure, because of constricting the input, reduces the pressure in the capillaries, and that would reduce glomerular filtration. Less pressure, less filtration. Just the opposite, if we dilate the afferent arteriole, then more pressure in the glomerular capillaries and more filtration, and that would increase the rate of glomerular filtration, which has a common abbreviation, GFR. Glomerular filtration rate. Okay, so dilating the afferent arteriole increases GFR, and constricting the afferent arteriole decreases GFR.
What is the rate that GFR is based off of? Is it like minute?
It's mils per minute. That's a rate. Mils of volume per minute. So similarly, if we constrict the efferent arteriole, if we limit the flowing out, that builds up pressure in the capillaries because we're not allowing the fluid to flow out as easily. And so constricting the efferent arteriole would increase GFR, and dilating the efferent arteriole sort of draws off the pressure here, decreases the pressure, and would decrease the GFR. By here we're decreasing capillary pressure, and here we're increasing capillary pressure. Okay, so, and we do all of this all the time. What cell type would dilate or constrict the efferent arteriole? Vascular smooth muscle. They are both arterioles. Even though one is going in and one is coming out, they are both arterioles, and so they both have arteriolar mechanisms for constriction. Kendra?
So a lot of people with kidney disease have like high blood pressure.
Mm-hmm.
So why would their GFR go down?
Typically, people with high blood pressure have renal disease. Their glomeruli have been damaged by the high blood pressure. So high blood pressure by itself, before there was any damage, would increase GFR. But the high blood pressure, the chronic high pressure in this, damages the glomeruli and leads to a chronic decrease in filtration rate, GFR, because of damage of those cell types. Okay, let's do another clicker. Which of the following, individually or in combination, would maximize glomerular filtration? Mostly seeing correct answers. C and D. A and B would be minimize glomerular filtration. So let's go back. Dilation of the afferent arteriole and constriction of the efferent arteriole would maximize glomerular filtration.
Okay,
Which of the following would decrease? Okay, this isn't just looking at, which of the following would decrease GFR? I'll give you the answer for one of these. I'll give you the answer for two of these. Multiple correct answers. Okay, good. I'm seeing Go ahead, Keisha, show me your answer. I'm waiting for you. Okay. All of them are correct. So constriction of the afferent arteriole, glomerular disease that I just answered by answering Kendra's question, those would decrease glomerular filtration. And if there is an increase in solute concentration in the blood plasma, remember solute in the blood plasma, more albumin in the blood plasma, more osmotic pulling of water from Bowman space back into the blood plasma, that would oppose filtration. So dehydration opposes filtration. Okay, let's take a break, and we're going to get to this concept of clearance. We'll need this for the quiz. So let's take a break and freshen up and come back and talk about clearance. Clearance is a process by which things are cleared from the body. And we have really two main ways of clearing things that we don't want from the body. There's renal clearance, and the material gets cleared out in urine. And there's hepatic clearance, and the material gets cleared out in feces. Those are the two forms of clearance. We are going, and that's because that's where we mostly excrete stuff, urine and feces. So we're getting into some nasty stuff, but that's it, excretion. We're going to be talking about renal clearance. I won't talk too much about hepatic clearance, but the principles are the same. So clearance, so let's think about excretion now. We've talked about filtration, now we're jumping all the way to the other end, excretion. There's a lot of stuff in between that we'll talk about next week. So excretion, how do we excrete something? Well, first we have to filter it. And then if we reabsorb it, that's less excreted. And if we secrete it by the tubules, by the peritubular capillaries or the vasa recta capillaries, that would increase excretion. So let me walk through it over here. How does stuff end up in urine? We can excrete it, we can filter it, or we can secrete it actively from the blood capillaries. Some things are actually both, filtered and secreted. Most things are either filtered or secreted. So those are the ways that things can get into the urine. The way that things like water and glucose that we don't want to excrete get out is they are reabsorbed. So the total amount that is excreted is what is filtered plus what is secreted minus the amount that's reabsorbed. Simple arithmetic. So now we have to work up some new jargon. The, quote, excreted load of something, X. X just means something. The excreted load of something is the amount of urine that is made per minute. This is a flow term. So this is not a volume term. It should be V dot. It's a flow term. Mils per minute of urine. Times the concentration of that stuff, of X, in the urine. Right? That makes sense. So we take a flow, mils per minute, and we multiply it by mgs per mil, we're going to get milligrams per minute. Or if we multiply it by milliequivalents per mil, we'll get milliequivalents per minute. And that is an excreted load. The excreted load is amount per volume. And it comes from the product, the multiplication of the flow rate, mils per minute, times the concentration, mgs per mil. That makes sense? And that product is called the excreted load. And I will ask you to learn this jargon. So let's do a clicker on excreted load. A person produces 1 mil per minute of urine. That's typical. The concentration of glucose in urine is 0. You don't have any glucose in your urine unless you're a diabetic. The concentration of sodium in urine is about 100 milliequivalents per liter. 100 millimole. That's typical. What is the excreted load of glucose? Good. A. You're doing the arithmetic in your head? 0.
Yeah.
What is the excreted load of sodium? Now you have to do some units conversion. Mill per minute, milliequivalents per liter. You've got to do this. You can do this in your head too. What is the excreted load of sodium? Show me your answer. How many liters, how many milliliters in a liter?
1,000.
So how many milliequivalents are there in how many milliequivalents are there in a mill of this person's urine? What's the number? 0.1.
0.1.
What? 100 divided by 1,000 is 0.1. So 0.1 times 1 is 1 milliequivalent per minute. Because if you chose 100, it's because you didn't do the units conversion. So be careful about the units conversion. Be careful, because renal physiologists will throw multiple units at you. Milliliters, liters, and deciliters. So we'll talk about deciliters in a minute. So now, finally, let's talk about clearance. It's a complicated concept. It's basic. I mean, there's a number of ways to think about it. There's sort of the physiological way to think about it. There's the arithmetic way to think about it. Maybe the simplest way to think about it is the clearance of something is equal to the excreted load of that something. We just did excreted load. The production of urine rate times the urinary concentration of the something, divided by the plasma concentration of that thing. That it defines the clearance. So let's look at the units. This is mils per minute. This is, let's just say, mgs per mil, in order to get a excreted load in milligrams per minute. And this is mgs per mil, if it's in the same units. So these two cancel out. And clearance, the units of clearance, is a flow term, mils per minute. Does that make sense just looking at this? We take mils per minute times a unitless ratio, and it's still mils per minute. Clearance is a flow term. But the way you calculate it is you take the excreted load of the substance that you want to calculate the clearance of. The clearance of substance X is the excreted load of substance X divided by the plasma concentration of substance X. That's an equation to know. I will ask you on a problem set to calculate stuff, and I'll ask you on an exam to set it up but not do the arithmetic. This, I will not ask you on the quiz to do arithmetic, so you don't need a calculator for the quiz.
I imagine you still want us to know this equation for the quiz.
Yes,
Okay.
you want to know this equation for the quiz, but you will not need a calculator. And some people like to think of, that the clearance is a volume term, so they think of it as a virtual volume, but I find that confusing. So let's play with this a little bit and do some examples. So here, here's a real simple example. Albumin. This is an example of albumin. Albumin is a protein. It is not filtered, and it is not secreted. It's too big to be filtered, and it doesn't get secreted. So the concentration of it in the urine is 0. So the clearance of it is 0. Okay? We don't clear albumin. If you have albumin in your urine, it's usually a sign of either exercise or glomerular disease. So there are simple tests for testing albumin in urine. Protein, it's called proteinuria, protein in the urine. Proteinuria can be a symptom of just exercise. So if you exercise and then do a urine test, you might find some albumin in your urine. Not a problem. If you have chronic albumin in your urine, that could be a sign of kidney disease. But clearance of albumin is usually 0 because we don't filter it and we don't secrete it. So there's nothing in the urine. So U sub X, U of albumin is 0. So clearance of albumin is 0. Okay, that one's easy. Here's another one that's pretty easy. A substance that is freely filtered but is completely reabsorbed by the processes that we'll talk about next week. So none of it ends up in the urine again. So if none of it is in the urine, the clearance is 0. This glucose is the perfect example of this substance. Glucose is small enough to be freely filtered, but we have excellent mechanisms in the proximal tubule, it turns out, for reabsorbing glucose so that we don't piss it off, pee it away. Urine, excrete it. We don't excrete urine. I mean glucose. We do excrete it. Let me say that again. We have excellent mechanisms to reabsorb all of the filtered glucose so that none of it is excretion. So the clearance of glucose is 0. We don't clear it. If you have glucose in your urine, it's a sign of diabetes. In Africa, probably not anymore, but there used to be a test in Africa for diabetes. They would ask the patient to urinate on the sand, and they would wait and see how many minutes it took for ants to come to the urine. If the urine had glucose, the ants would be attracted, and they would come. And if the urine was normal, it doesn't have glucose, and the ants couldn't care less about it. It's actually a pretty good test.
Yeah.
Okay, so now let's get into sort of a generic state. A substance that is freely filtered, but it is not reabsorbed, nor is it secreted. Okay, so let's do that again. Substance is freely filtered, but it is not reabsorbed by the tubules and the capillaries, and it is not secreted by the capillaries. So everything that ends up in the urine is what was filtered. Now remember, clearance is a flow rate. Filtration is a flow rate. So in this special case of a substance that is freely filtered and is not processed, the clearance of the substance is a measure of the glomerular filtration rate. So, for example, you have in your body right now a substance in your blood called creatinine. Creatinine is a breakdown product of muscle metabolism. And it is in your blood at a certain concentration, and it is small enough to be filtered, but it is not reabsorbed. So we clear it. So we could measure creatinine clearance, because we could measure the flow rate of urine, V dot. We could measure the urinary concentration of creatinine. That would give us the excreted load of creatinine. And we could measure the plasma concentration of creatinine in a blood draw. And by dividing the excreted load by the plasma concentration, that would calculate us the creatinine clearance. And because of the properties of creatinine clearance is a measure of GFR. So when you have blood work done in the hospital, and they want to know what your GFR is, they do it by creatinine clearance. There are other more sophisticated tests that require actually infusing stuff into your bloodstream that are more accurate than creatinine, but nobody does it. Creatinine clearance is taken as a measure of GFR. Is that clear? And why creatinine? Creatinine clearance is a measure of GFR because it is freely filtered and it is not reabsorbed and it is not secreted by the renal tubules. It is not processed after filtration. So what ends up in the urine is what got filtered. And that's why clearance of creatinine is a measure of GFR. Is the clearance of glucose a good measure of GFR? No, it's a terrible measure of GFR because glucose clearance is 0, usually. Is the clearance of, well, let me do the next one. Creatinine is a good measure of GFR because of its special properties. It is filtered but not secreted or reabsorbed. Is that clear? So if I ask you to calculate GFR, you immediately go to the creatinine information. You don't pay attention to the glucose information. You don't pay attention to the sodium or the potassium or the albumin information. You pay attention to the creatinine information. Okay, here is another special case. Actually, let's skip this one. We'll come back to this one. Let me go to the next one. Here is your generic case. A substance that is filtered, freely filtered, and partially, not completely, partially reabsorbed. So some of it is cleared, and some of it is reabsorbed. Freely filtered, partially reabsorbed. This is what you do with your sodium, potassium, bicarbonate, phosphate, urea. Those are the main components of urine, actually. So in this case, if this is the generic rate, some of it is filtered. It's freely filtered. It's partially reabsorbed. Now the clearance of this substance is simply defined by the clearance equation for that substance. So is the clearance of sodium, so let me just tell you, sodium is partially reabsorbed. Is the clearance of sodium equal to GFR? No, because to calculate GFR, we have to have something that is neither reabsorbed nor secreted. And sodium violates that because it is partially reabsorbed. So the clearance of sodium is not a good measure of GFR. It's a measure of other things. Okay, so most of the things that you urinate have clearance, and the clearance of that substance is simply defined by the clearance equation. Is the clearance of sodium likely to be greater or less than GFR? Less, because some of it is reabsorbed. So some of it is not here. So the urinary concentration of that stuff is lower than if it were not processed. And so the numerator here is smaller. We don't have any information about the denominator, but so the clearance of sodium is less than the clearance of creatinine. It's less than GFR. There is one special case where a substance is freely filtered, it is so actively secreted that none of it ends up in the veins. All of it ends up in the urine. All of it ends up in the urine. And in this special case, the clearance of that substance represents the amount of plasma that goes to the glomeruli, which is the renal plasma flow. let's not let this special case confuse you too much. And we'll come back to this next week. You won't need to know this for the quiz. This is the general situation. I'm going backwards. This is the special case of creatinine. This is the special case of glucose. This is the special case of albumin. Okay, so I started with some special cases because they were simple. But this is the generic case, the general case. This is the slide to pay attention to if you don't know. If it's not glucose, and it's not albumin, and it's not creatinine, this is what you use. Okay, so let's do some of these problems in class. You will have a problem set where you'll work on this some more. But again, you want to know the principles for the quiz, but you will not need to do arithmetic. Okay, so let's do some of these. We've got 5 minutes. Let's go ahead and use your time. You paid for it. So here we have a case. Plasma creatinine is 1 milligram per deciliter. Okay, here's another one of those volume terms. A deciliter is 100 mils, 1/10 of a liter. So don't let deciliters screw you up in the calculation. You have to change this. So 1 milligram per deciliter is 1 milligram per 100 mils, which is 0.01 mg per mil. Okay? Deciliter is 100 milliliters. A liter is 1,000 milliliters. You'll have to just know these things. The urine flow rate is, in this case, 1.1 mils per minute. The creatinine concentration in urine is 0.95 mg per mil. So, get out your calculators or your phones. What is the clearance of creatinine?
No, it isn't. So, a deciliter isn't it 0.1?
Somebody give me a number. Please. Okay, 104.5. Okay, there's the units, 104.5 milliliters per minute. What is wrong with that number? That's probably the number you all got.
Yeah.
What's that?
No.
104.5 is the number you all got. How many significant digits are you given? 2. What is 104.5 in 2 significant digits? This is a little tricky. It's 100. Because you would round you'd round 104.5 down to 0, so that would be 100. Okay, so I've made such a point of it in class that maybe I will ding you if you give me too many significant digits.
No.
It's a thing. It's a thing. It's a real thing.
You're off.
So, with 2 sig figs.
What?
If you were to represent with 2 sig figs, then would you want us to write it as 1.0 times 10 to the second?
So, Tynan is pointing out that significant figures are more easily described in scientific notation. And so, there's an ambiguity in significant figures, right? 100, you could think of 100 as 1 significant figure, or 3 significant figures. So if I draw like that, that is 100 to 3 significant figures. If I draw it 100 like that, it's 100 to 2 significant figures. And if I do it like that, it's just 1 significant figure. So there isn't an ambiguity. Nobody does this anymore. Nobody does this anymore. In fact, you probably have never seen that, but that used to be a thing. The point is, 100 is a correct, I will probably manipulate the numbers so that we don't have the ambiguity between 2 significant figures and 3 significant figures. But in this case, the best answer to 2 significant figures would be 100, not 104, because that's 3 significant figures, and not 104.5, because that's 4 significant figures. Okay? So significant figures is a thing. What is the GFR? So the clearance of creatinine is 100. What is the GFR? 100 mils per minute, because the clearance of creatinine is a measure of the... so let's not do any more. We're not going to do PAH because that's a special case of plasma flow. I guess I recommend doing this as homework, just to solidify your understanding of clearance, filtered load, and excreted load. Filtered load. Did I tell you what filtered? I didn't tell you what filtered load is. Let me just think. What's that?
It's on the
Is it on one of the slides?
Yeah.
I don't remember saying anything about it. Did I not say anything? Oh, here it is, right there. Once you know the GFR, you can calculate something called the filtered load. It's the GFR times the plasma concentration of that stuff. So the excreted load is the urinary flow times the urinary concentration. And the filtered load is the filtered flow, GFR, times the plasma concentration. Those are things to know for the quiz. Okay, so I'll see you in lab this afternoon or this evening, and we'll do kidney anatomy.